Yeah, hello, Kirtan, I'm audible.
Yes,
Uh, all right, Kirtan. So in the last class, what we started with, we said we are starting EMI, electromagnetic induction. We started by saying about the Faraday's law. We studied a little bit about the Lenz's law also, and we did a one problem also, right? That was not a problem, just a concept we studied a little bit. So I'll extend the session by one small problem, continuing with the previous part itself. So example here I'm going to take again the similar example which I took in the last session, but in a twisted way. What is that? This is again straight wire having some current I. In the previous problem, I said there's a loop, rectangular loop. It is placed at some distance. So you need to tell. I don't know what it to tell. Like there was some force on it. It is for yeah. Here the current was varying. Right? This was the case in the previous problem. So now what happens is here this current is fixed. Okay, fixed current. Okay, that's not bad. Now what I'm saying is this frame has some mass m. Okay, yeah. So you need to calculate, and there is a velocity. Right now, this frame has a velocity in this direction is v as a given direction. Okay, so you know that this frame is going away from basically away from this thing, right? Here, this current is constant. So you can simply say that, sir, because this current due to this infinite wire is varying. How it is, no, the current is same actually. Magnetic field is different at every position. For example, here it is different, here different, here different. Why? Because B is inversely proportional to R. So more you go apart, more the distance will lose. So let's think in one way that due to this current, the magnetic field is going to be in this direction. Right? We are not talking about the magnitude force right now. We are just talking about the what if I can say that is field direction. Because this is what the field direction will be. You also know because this frame is going away from this, what is going to happen? Uh, will flux change? Yes. Why? Assume that at this, if I take this part earlier in this portion, magnetic field was something else. But when you take it here and when this reaches somewhere here the magnetic field value is decreased. Why? Because this is at some distance x, this is at some distance x plus dx. So you know that the magnetic field is inversely proportional to x. So previous case like this, after that case like this. So this is a lower value. It's basically at each point magnetic field is increasing because you are moving apart. So I can actually say the flux is changing. Understood. So what will happen over here? Just look at this. Because magnetic field is decreasing by the time. So should I say the flux is decreasing? Yes, makes sense. Because magnetic field is decreasing, I can simply say in this picture that flux is also decreasing. Yes, makes sense. If flux is decreasing, I know this changes in the flux induce a current I induced. Okay, how it is going to induce? To support the magnet. Why support? Because to support or you can say flux. Why? Because it is decreasing. It means I need to support it. Okay. Magnetic field is inside direction, but it is decreasing. It means I need something which can make current in this direction. Basically, magnetic field in this direction. How I can make it? By keeping a current in this direction. If there is some current induced, come up into the picture like this, then I can have it. Okay, makes sense. You know this current has assumed, so anywhere if you want, you can create a EMF. Let's say this is the EMF due to which this current has been produced. Okay. That's how we can think about these kind of problems. What's next? Now look, what is the case here? Now I can say because it is the velocity is changing by the time. Okay, it is regularly, it is moving, right? It means flux is regularly changing. It means there will be a regular current. Okay, although this current I induce is going to change by the time because the change in flux is different at every position, right? So it is also going to be changed. At this point, the moment current is there, you can see there is a frame, this wire, which is having some I induced current, but this is present in a magnetic field. Okay, it makes sense. A wire having current in magnetic field appear what I can say. Mm, yeah, there always some force on a wire when it is present, when it is kept into a magnetic field, and if it is carrying a current. Okay. What is the direction of force on it? Again, simply you can just use your right hand palm rule. All the fingers towards magnetic field, thumb towards your whatever I can say. Current, where your palm is showing upside. It means on this frame the current magnetic force is upside. Force on this frame is up. What about the bottom force on this downside? Why? Because magnetic field here is this, like current is in this way, this and this. What about this one? Sorry. Here it is like this, here it is like this. Makes sense. Now you will say, sir, all of them are getting cancelled. No, it's not getting cancelled because on this frame it is same. Because here magnetic field, here at any instant if you see magnetic field is same, magnetic field is same. So then this means force at this point get cancelled, force here and here cancel, here and here cancel. That is fine. But what about the vertical fields? Magnetic field on this portion is greater than this portion. It means force on this is greater than this. Understood? Force on left is force on right. Force on left is greater than force on right. It clear? What this will create? This is going to create a net. What is that? That will be FL minus FR. You can call this as F net. If there is a F net, that will produce an acceleration. F net by M. This acceleration is again varying, but we'll see what is the variable value in future parts. This acceleration is now, there's an acceleration on the object. Okay, makes sense. There's a body, there's a velocity, there's an acceleration. Okay, so this acceleration will try to stop this value, stop this object. Understood? How? You know, if there's an object, it will take some time, but after that, it will get stopped. Understood? This is how things are going to work. I hope this is clear. Let's take one more factor. Assume that after some time, maybe here, this frame reaches like this, and here the velocity becomes zero. You know why it becomes zero? Because there is an acceleration, right? Okay. So because this has stopped at this point, it is not moving anyways. It means at this point, the moment it is stopped, just call B downside, this upside. Okay. Here what will happen? B is zero. No, B is constant. Flux is constant. Okay. This is at this particular place. So what will happen here? The induced will be zero. Understood? If induced is zero, nothing will happen. It will stop like this. Okay. So the problem can be framed in a such a way that they may ask you, what is the distance you have covered, what is the time you have taken. Okay, these kind of things they can ask you. So if I ask you, Kate, now can we solve something? Yes. If you could remember, let's talk about the total energy of the system. This object only has what is the initial energy? Half mv square. Anything else was there? I can't see, right? Only this much energy. When it reaches here, its velocity becomes zero. It means you have used all of your half mv square. This energy has been converted. Can I say this I induced from where it was coming? If you see, this was coming from the object's energy, right? So we can say the whole energy, whatever the current induced and everything, the average current which you have induced, that is the result of this thing, right? So we can simply say half mv square is nothing but 0 to some value I square r dt. Basically, your current this time, how much time you took from here to here you reach, right? So you have basically converted everything into the electrical energy. So that's how you can actually solve the problems. Understood? Let's move to the next part. Look, if you want to say, sir, how we can complete this problem, basically you are going from zero to infinity. Okay. Um, at the last, even if you see the current is still zero, in the start also it was zero. What will happen? You need some I. in the form of time. Okay, you are going to put that equation, then we are going to substitute it and get the answer. This is how we are going to solve this problem in the future. Okay, these kind of things we have to observe. It's about how we are going to observe the problem. Okay, so assume I'm giving you another problem. There's a loop. Think of a conducting loop. This is conducting loop. Okay, this is fixed. Loop is fixed. Okay, we are not going to move. This is axis of it. On this axis, I have kept a magnet. Okay, you know this is not full. This is not full. You know if magnet is kept, there is magnetic field. This kind of thing is okay. So अब मैंने क्या किया like sorry. Then from here what I did is yeah, whatever. I kept it and then I said let's give a velocity v to the magnet. Look, don't consider magnet gravity in this it will fall down or something. Leave that thing right now. Just think about magnetic force and all. I have given this velocity v. Okay. Then you can say that flux is also changing, right? So while using Lentz's law, we know that there will be flux changing. I'm sorry, by the Lentz's law, it is going to oppose the change. So we know flux is changing. It is going to oppose the this loop is going to induce some current. Okay, but how it is going to happen? This is what we need to discuss in this problem. So think of it once. You have a loop, right? Because the object, this magnet is going away. It means the flux which was linked with you like this, it is decreasing. Okay, it is decreasing mean to say you need more current to get into this direction, right? Because it is decreasing, you need current such a way that it is going to produce magnetic field like this. What I can say, yes, you can make this kind of magnetic current. I induced should be in this direction so that it will produce a, it will actually produce some current. Okay. Again, so if you see the problem is similar to the previous problem because object is going away. But in the previous problem, if you could remember, my this object was itself moving, right? So producing the current and everything provided acceleration to this object. But in this particular case, this object is not moving, right? So what will happen over here? Just think of it once. This object is moving, okay? There is a current. So because there's a current in this loop, let's look in this. I'll make like this. Now think of it. Magnetic field is in this way, yes, because if you see from this way, you will look like this. Magnetic field is going inside of this loop, right? Due to this, we had a current like this to support this because magnetic field is decreasing. Because this whole thing is kept into a magnetic field, there's a wire. On the wire, there will be force. What is the direction of force going to be? Force is going to be outside. Makes sense. So what will happen? All these forces are going to cancel each of them. Why? This force gets cancelled by this part. This force gets cancelled by the directly opposite one. This force is going to be cancelled by opposite one. In this look, in the previous case, there was a concept that force here is greater than force, but here it is also not the same. Why? Because all the points are at equidistance, right? This point and that point, all of them are equidistant, right? So that is also not the case. So what will happen is net force on this is also zero. Okay, let's remove it once. So basically, when the current is going in this one, so you can assume this kind of configuration. So what can happen over here? So now what you can think is because you have a current now, like you have a magnetic field inside. How? Because of this loop, right? Can I say that because there is a current, sorry, there is a current in it, I there is a magnetic field due to that current like this. Okay, what kind of magnet I can expect? You know, a current carrying loop act as a magnet when it's small or something. How? Because there's a current, right? Magnetic field. Because current is inside. When you are inside the magnet, current goes from south to north. So it is going from this to this. It means this is south, this is north. Can I say this is acting as a magnet itself? Yes. So the now the configurations looks like you are having a small magnet over here. Basically, this is the due to the loop, right? This basically there was a loop, current I induced. So here you can say I current was there, induced current. There was a magnet over here, north and south. Okay, and this was a field due to this, and it is going away. Makes sense. If it is going away, you know this pole is attached with this pole also, right? Can you see this? Are you getting this point? If this kind of configuration formed, can I say this south is getting pulled toward this? Yes. All right, now just look at this ones. Because of this velocity, like there is a velocity, there is a force. What kind of force? Due to this thing. You know that this loop is fixed. So is it going to move? No. If it is not going to move, what will happen is, look, if it was able to move, it could have started moving until unless their velocity gets same. But if because it is not able to move, what will happen? There will be force on this object. What kind of this kind? Now you can see the object magnet is like this, velocity is like this, force is like this. What is the force? Mass into acceleration, right? From here you can get acceleration is F by m, whatever the net force between the magnet comes out, right? You also know that the force between two magnets is nothing but F is equals to what is that? Mm, oh, basically you can simply say mu naught by 4 pi, two poles basically. That's all this is m1, m2 divided by r. Okay. This kind of thing we can expect over here. That this kind of force will be there, right? Dividing the whole thing by this mass. So that will actually results you out with the acceleration of mu naught by 4 pi m2 divided by r. So this kind of acceleration you can expect. Because of this acceleration, you can say your object will start moving like will have a negative acceleration basically. This acceleration may or may not provide this velocity to zero. This will make this velocity to reach zero. Just a second. Okay, so this kind of thing is going to happen. Any doubts so far? Okay, in the same case, this velocity is going to reach zero. The moment it goes to zero, the velocity is zero. At this moment, the relative distance between them will decrease. Okay, so acceleration will also decrease because the moment this velocity goes to zero, right? The flux change in this loop is going to be zero. The moment this goes to zero, because there is no change, the induced current will zero. If induced current will zero, this magnet will vanish because you have vanished this magnet. The moment this magnet will vanish, there will be no acceleration. Okay, these kind of things we need to understand. Okay, so let's do one more thing, that is assume Kirtana, you are having a single loop. Okay, what you did, you had a loop. So this kind of loop you had. Okay, this kind of loop is there. What I'm doing is I'm having a magnet at the top, just like this. In the effect of gravity, in the effect of gravity, basically I dropped this from the top. Dropped. I didn't throw it. Okay, I'm just throwing. I'm just letting it to go down in the effect of gravity. ns. Now what will happen, Kirtana? Look, it is falling downside. It has some acceleration which is equals to g. Initial velocity is 0. You know, at this position there will be some linked flux, right? Because it is getting downside, its flux is going to increase. Because flux is going to increase, you know, there will be induced current. Why? To oppose the increase. It means your induced current will be such that it can produce flux in this direction, magnetic field in this direction, right? So what I can say, the induced current will be this way. This induced current will make an opposite direction. What I can say, it is going to act as this kind of magnet, south, north, south. Now what will happen? Because you have kept it fixed, it is falling from downside. What will happen? Earlier, because of zero velocity, it has zero velocity, so it was not falling, but it has acceleration. So due to acceleration, it is falling downside. It must be gaining some velocity. Okay, understood? It is going to gain some velocity. But what will happen is, because it is getting closer to it, okay, flux is increasing more and more. So there will be some force on this. Why there will be force? Because this is acting as a magnet. This is not pull, this is not pull. There will be force on this. F, F. So now you can say on this object, there is one force downside which is mg. There is another force that is F. So mg minus Fm is there. Initial velocity is 0. So this object will fall till this velocity becomes 0. Like initial velocity was 0, final velocity is also should also be 0. Or you can say this will make this object to fall, but it will not be able to reach its maximum velocity, which it could have easily reached. If you could remember, there's some bamboo or copper item, right? If you pass a like assume you have a copper bottle or something, or hollow copper, it means, okay, if you pass a magnet from there, what will happen is, in general, if you throw a stone, it will fall down and a very, okay. But if you throw a magnet, what will happen is, it will take much time to pass from it. Why it is going to take much time? Because if you could see, initially there is no flux. You are putting a magnet at the top. It means there is some flux. When it is going closer, when it is going closer, there is some force on it, right? There is some apparent force F. So the net acceleration on this object gets reduced. Understood? So what happens is, if you simply throw a normal stone, non-conducting stone or something, there's no effect of magnetic field and something over it, so it will directly fall down with acceleration. But in this case, even though this, what I can say, yes, look, if the monopole or something is very strong, then it will stay upside. Otherwise, if it's not that strong, monopole is not that strong, then what will happen is, simply it will fall down, but the net acceleration will not be equal to 0. Okay, so here, force on magnet will be Fm upside. So Fnet will result in mg minus F magnetic force. Okay, this kind of thing is going to happen on the object. Clear? So look, this is upside case. Now assume it reaches at this point and it will start falling down. Because you can see the moment it reaches very close, there will be very high force. It will make the velocity to go downside. Understood? It will make the velocity to go downside or maybe near to 0. Okay, it will never make the velocity 0, but the moment velocity goes 0, acceleration goes 0, you can say acceleration is also always there, but velocity goes 0. So after this, let's say loop reaches to this state, magnetic north, pole, south. Now look, this object want to go outside. In this case, at this particular case, it has maximum flux length, right? It has maximum flux length. Okay. So now what will happen is, this object is trying to move away. It means flux is decreasing. In this case, the current will in opposite direction, which will make the opposing current. That will provide a magnetic field, magnet like this, north this side, south this side. This is going to attract now. This attraction will make it to no fall downside of it. Look, upside we said there is a force on the magnet. Upside when magnet was there was a force upside which was decreasing its acceleration. Downside, there's an mg, and there will be force Fm outside, okay, which will decrease its acceleration. So basically, on the whole path, okay, if it is going from top to bottom, it will not be able to move with a maximum acceleration g. Okay, it will be having lesser acceleration somewhere. Okay, that is how things are going to work in this. I hope this is clear to you.
Yes.
Um, so let's okay. So let's talk about morals of Faraday's law. So look, by Faraday's law, we have already got that E is equals to, this is EMF. Okay? EMF is basically minus df by dt. Okay, why this E is in the negative? Look, why this is negative? Because my EMF is going to generate in a such a sense to increase it, right? Assume my flux, change in flux is amount some amount, okay? It is in this direction. So EMF will be generated in such a form that the new flux of a same amount forms in support of that. Okay, this assume this amount was decreased. It means you need to put another this much amount. Okay, decreasing is negative direction. So that's why we are keeping it negative. We have to support it. Okay? That's why it is negative. If flux change is positive, the whole thing will eventually get negative. What does that mean? This EMF has come across because this whole thing comes out positive because change in flux is positive. In that case, the EMF is to decrease the thing. Okay, if it is decreased, it means the whole thing is negative. It means it is in the support of it. Clear? So let's solve the problem. It will be much better. Okay? So you are given basically, let's solve it. You are given a conducting loop. Okay, this is one thing. It has a radius r and has a n number of turns. Also, Kirtana, the whole wire has a resistance of r. R is resistance. The complete wire. Okay, there's a magnetic field in this direction inside basically. This kind of magnetic field is there. Understood? And what is the value of magnetic field? This value of magnetic field is V is equals to B not T. It means this magnetic field is changing with the time. You know, if the magnetic field is going to change with the time, there will be some current induced, right? This is the thing we have. So you need to calculate, find induced EMF on the load. This is what you need to calculate it. So can you calculate that? Try it once and let me know the answer. Okay, you need to calculate induced EMF or induced current, both of the things. You know, if you get the one thing, you'll get the another thing. Yeah, Krishna, you're trying to solve it, or should I give the solution? Please let me know once.
I'm solving.
Okay, solve it and then get me the solution.
So can you explain?
Okay, makes sense. I know. I know. Okay, let's look at there's a current. Okay, and the current value is this much. It means it is direct. No, sorry, magnetic. What is a flux? Flux is nothing but because area. What is the area right now? Flux is nothing but B dot S. If you see at each point, magnetic field is constant, right? Each point it is constant, but by the time it is changing. At if you see at some time t, it is constant. At any time it is constant at all the points. Okay. So magnetic field is this. So flux, the net flux is nothing but what is the B? B naught times of t multiplied by pi r square. Sorry, radius is square. So this is r square. So this flux is nothing but I r square t. Varying flux, right? What is magnetic electric EMF? It is nothing but change in flux divided by time. Because flux is increasing, because time is increasing, flux is increasing. You can simply put minus. Look, two ways are there. Okay, two ways are there. Simply go with without any putting negative. That will give you the absolute item. Let's see. Do a differentiation of this. You are going to get B naught pi r square t. What does this mean? This is giving you magnetic field value. Okay, but you don't actually know the direction. Let's see. Until unless look, if you are given a visualized figure, you can actually visualize the thing and do it by yourself. If it is not, even go with the proper sign convention. Here I have given visualize. The thing is increasing, magnetic flux is increasing. It means my EMF is going to induce such a way that it is going to decrease the flux. If you know current is magnetic field is decreasing out inside. Okay, so my flux, my EMF will be such a way that it can produce some current which may produce magnetic field in this direction, right? So to get magnetic field in this direction, what kind of current I need? I need a current which can go in this direction. Current is going in this direction. What does this mean? There must be some EMF in this format, right? You can say either this format or either this format. Wherever you want it to put, it's your choice. Keep it is like this. This is EMF. Okay. So yes, I have got the EMF. So EMF is nothing but B naught pi r. Sorry, this is R square. And what is the current? Current is nothing but total EMF divided by the resistance. And you know, resistance is for this one is given as R. So this is pi r square divided by capital R. Clear? So if you see carefully, because the current is magnetic field is changing with the time with only directly proportional to. So here, whole the time you will be having same current, okay? Same induced current. You will say, sir, why only same induced current? Because you can see this thing depends upon the change. Assume because the same thing is there. If I'm looking from time is equals to t is equals to 1 to t is equals to t. So what is the change I'm going to get? Magnetic field will be changing from assume V naught to what is that? V naught to 2 times of V naught. So what is the change? Only V naught. From here to 3 V naught, basically time is 3. So this, if you see the change is constant. So that constant, for that constant change, you need a constant thing, okay? Because here the change is constant. If I make a different position and if I say instead of T, the magnetic field is T square, okay? If B is equals to V naught T square, then what would happen? The flux would be B naught pi. Sorry, let's use another color for this thing. This is another part, okay, for the same problem. So I'm using another data. If B naught is equals to B naught times of T square, it means here, if you can see, the magnetic field is only dependent linearly, okay? Here it is not. Then flux would be B naught pi R square T square. EMF will be change in flux. If you could see here, B naught pi r square 2 times because if you differentiate this, you are going to get t. Here your EMF is changing. What does that mean? because right now this is not linear. What does that mean? When time was 1, magnetic field was V naught T square, right? This results to V naught. When time is 2, this becomes B 2 to the 4, 4 times of this. It means what is the change in 1 second? In the first 1 second, what is the change? 3 times of B. After this, when time is 3, that is 9B. It means because 3 3 is a 9. So what is the new change in the another 1 second? We have got 9 minus B, that is 6. After that, 4 to the 16, 16B, right? What is the new change? That is 7. So here the change is also varying with the time. Understood my point? Here the change is also varying with the time. So you need this thing. Okay. It will be a varying. Clear? Understood? And what is the dependency of that thing? That change dependency goes on the value itself. Okay, so that's how you have to solve the problem. Clear? Any doubt is there?
Yes.
No doubt, right? So, Kirtana, let's do one last problem and we'll end the session today. So, you are given a basic rectangular loop. This is circular. I'm going to give you a circuit. This is a battery. This is a battery which we have already kept. Okay, resistance of whole loop is R, and this battery is 20 volt. Now what I'm going to say this, okay, this is 90 degree, this is 90 degree. This is 2 meter, okay, and this is 3 meter. This length is 3 meter. Now I'm saying in this fluid there is a magnetic field B is equals to zero point 0.5 Tesla in multiplied by time. It is dependent upon Tesla inside. So Kirtana, in this case you need to calculate what is the current in the circuit. Solve it once and let me know the answer. Kirtana, you have got the answer, or should I solve this? Yeah, Kirtana, should I give the solution or you're solving it?
Sir, can you explain?
Okay, look. So it's an easy problem. I don't know why you're not able to make it. Look, there's two ways. Okay. You know, this 20 volt is there. There's a current due to this, like this. Something current will be there. We are not bothered much about it. Okay. So that due to that, there will be magnetic field that is constant inside. Okay. So do we really need to bother about this voltage? I don't think so. We can simply go and calculate what is the contribution of this thing, this change. Okay? So simply, you know, what is that? Magnetic field is zero point 0.5 times of test time. Okay. Flux is nothing but area into B. So what is that area? 2 into 3, that is 6, into 0.5 times of T, which results out how much? 3T. This is the magnetic flux we are going to get. What is the actually name of that is d phi by dt? That is 3. This will result in 3. You know carefully that your magnetic field is changing. Flux changing means to say you need EMF which can oppose this flux, this change. What does this mean? Right now your flux is in this way. Okay, this sorry. Your magnetic right now, yeah, flux is in increasing right side, right? So you need a current. I'm not talking about what is the current due to this. I'm talking about what is induced part. What should be the induced part? So induced should be in this way so that it can oppose the current, okay? Because it can make it like this. Your current is going outside, so this will produce a current which can form like this, okay? So due to this induced, you can say this is induced, it means there must be some battery. So you can say the battery might be looking like this. Okay, what is the value for that battery? That is 3. Now you will say, sir, I need to calculate the net current. Can I say the net EMF in the battery is nothing but 20 in this direction, 3 is in this direction. Then that comes out 20 minus 3, that is 17. So what is the current net? That is 17 by 17 by 5, that results to 3.14. Now you will say, sir, why 5? This. Now you will say, sir, what is the direction? The direction is this. I is equals to 3.14. Now you will say, sir, wait, this current is actually supporting this magnetic field. So how we are going to oppose it? Yes, we are opposing it. How? If this thing would not be here, what would be the answer? 4. Why? 20 by R is equals to 4. 20 by 4. So basically, what you did is some current was there. This lesser part of the current has been produced, which is actually producing less amount of current. How? Because earlier, due to this 20, there was already some current, right? There was some current already, some magnetic field is already there. Now your field is also increasing, field is increasing, field is increasing. So this increasing field, what this is doing, this is providing some oppose. So here this oppose was like this current itself get reduced by some amount, but this was very high, this constant current was very high, large. So you can only see this part that this is reduced amount of current. Okay. So this is what you are seeing over here. This is changing. Here this amount has been less. Okay. So that's what we are seeing. So basically, this EMF is providing its all contribution, although whether the whole thing get opposed or not, that is a different case. But its contribution is this much. Okay? So you can simply say this is going to be the answer. Is that clear? Ethan, is that clear?
Yes.
Any doubt?
Yes.
No doubt, right? Okay, look. What you can do. All right, Kirtana, that's all for the today's session. Rest problems we'll be discussing in next class. Okay, goodbye. If you have any doubt, please let me know. I'll explain that and then I'll end the session.
No, that's
No doubt. Okay, then we can actually end the session.